I'm Rowland Shelley in the Department of Entomology and Plant Pathology at the University of Tennessee. I have been researching the megadiverse arthropod class Diplopoda or Millipedes for nearly half a century and want to share my theory of the class's origin and early evolution, which is rooted in three basic facts. First, the molecular analyses by Pisani 2009, who dated the origin of Diplopoda at 524 million years ago in the mid-Cambrian period Paleozoic era. Secondly, tectonic movements dating back to the Cambrian that are based on geological evidence. And thirdly, documented millipede distributions that are based on localities of preserved samples in worldwide collections. My theory is based largely on geography or distribution. Geographic considerations are often maligned and even derided despite their fundamental importance. Where taxa do and do not occur yields valuable insight into their origins and biology. Distributions or geographies tell a lot about organisms if we just open our eyes and minds to receive the messages the information sends us. First, a few relevant basic facts about Diplopoda themselves. Diplopoda is a definite monophyletic group with a single origin at a single place at a single time. Millipedes are mandibulate arthropods that are highly specialized and adapted for burrowing. Some forms have abandoned burrowing for different lifestyles, like being surface active or cryptic and inhabiting existing cracks and crevices. Millipedes are poorly vagal organisms that can neither run, fly, swim, nor float. Their widespread distribution has thus been achieved by riding tectonic ferries. The oldest millipede fossils are from Silurian terrestrial deposits in Scotland that have been dated at around 420 million years old. Diplopoda are characterized by three autapomorphies: aflagellate spermatozoa, four or more apical sensory cones on the antennae, which is what they're tapping when they're walking and tapping the antennae, and the big one, the diplosegment condition, a strong modification for burrowing in which alternate body somites become fused within the embryo to form diplosomites, and the pair of legs, the pair of tracheal openings or spiracles, and the ventral nerve cord ganglion associated with the anterior somite have been relocated in the posterior somite, so that in the resulting diplosegment, shown in the top figure, all four legs, all four spiracles, SP, two on the other side, and both ventral nerve cord ganglia are located in the metazonite, M, representing the posterior of the fused somites, while the prozonite, P, representing the anterior of the fused somites, is without structures and can therefore insert inside the caudal end of the preceding metazonite, resulting in a telescoping of segments and a more compact body form. Now, Sidney Manton, the late British functional morphologist, showed conclusively, in my opinion, that the diplosegment condition evolved in conjunction with millipedes' burrowing habits, that the pushing force is more efficiently transmitted to the pushing surface when alternate segmental joints are made rigid and incompressible. The power for the pushing comes from the legs, and at any point in time while walking, most of a millipede's legs are on the ground in stages of the backstroke, pushing the animal slowly and inexorably forward. In the diplosegment figure, O shows the ossipore, the opening of the defensive gland just below the exoskeleton. A few basic facts about Earth's geological history. There is a supercontinent cycle in which all land masses assemble into a single giant supercontinent, rift apart with the fragments drifting on the Earth's magma layer, and reunite periodically. 7 supercontinents have been postulated in the Earth's history, the most recent being Pangaea, which formed 250 million years ago in the Triassic, existed for about 100 million years, and rifted in the Jurassic into large northern and southern continents, Laurasia and Gondwana, respectively. The last supercontinent prior to Pangaea was Pannotia, which formed around the South Pole 600 million years ago and rifted in the early Cambrian period, 560 million years, into 3 northern microcontinents, Baltica, Laurentia, and Siberia, a group of islands, one being Kazakhstania, and a giant southern continent, Gondwana. Today, Kazakhstania is in Kazakhstan, Siberia in Siberia, Laurentia in North America, and Baltica in Northern Europe. So there are two Gondwanas that are similar in composition but vastly different in significance for millipede evolution, and they have to be distinguished. I therefore call Pannotia Gondwana Gondwana 1 or G1 and Pangea Gondwana Gondwana 2 or G2. On the left is a map of the Earth 600 million years ago with Pannotia cupped around the South Pole and the three future northern microcontinents, Baltica, Laurentia, and Siberia, attached to the landmass. 524 million years ago in the late Cambrian, in the inset, they have separated and drifted northward, and a scalene triangular terrain, Abylonia, is attached to G1 at the juncture of Proto-Africa and Proto-South America. As shown in maps taken with permission from Christopher Scotesi's Paleomap website, 458 million years ago in the mid-Silurian, Abylonia, which is carrying ancestral millipede stock, has rifted from G1, drifted northward, and is approaching Baltica, with Laurentia, Siberia, and Kazakhstania to the north, and a terrain of land that forms today's northern China has rifted from eastern Gondwana 1 and is drifting northwards towards an eventual collision with Siberia and Kazakhstania. 425 million years ago in the late Silurian, Abylonia and Baltica, which merged 450 million years ago, combined with Laurentia 440 million years ago to form Euramerica. Meanwhile, the North China terrain is advancing towards Kazakhstania and several additional terrains that will eventually form all of today's eastern and southeastern Asia and much of Indonesia have rifted from eastern Gondwana 1 and are beginning to drift northward. There are Malaya and South China terrains with more to come. On the left is Pangea in the early Triassic, 260 million years ago, with eastern and southeastern Asia completely formed with Malaya and modern Indonesia attached as a peninsula. In the late Jurassic, 100 million years later, Pangea has rifted into Laurasia and Gondwana 2. Note that the Southeast Asian Indonesian peninsula is part of Laurasia. These lands formed from terrains from Gondwana 1 and carried Gondwana millipedes northward, but when Pangea split, they became part of Laurasia, the northern continent, not Gondwana 2. So here are four important points. Paleozoic drift patterns ran from south to north. I know of no terrains that rifted from Baltica, Siberia, Laurentia, or Laurasia and drifted south to either Gondwana 1 or 2. Consequently, a monophyletic group that occurs globally today and can neither run, fly, swim, nor float had to arise in the south on one of the Gondwanas. Had it originated in the north on Baltica, Siberia, Laurentia, or Laurasia, Diplopoda's present indigenous distribution would be quite different and primarily restricted to the north to progeny of Laurasia. A brief taxonomy of Diplopoda to the ordinal level. The class comprises 16 orders and around 142 families today. The number of component families of each order is shown by the numbers. Diplopoda is divided into two subclasses. Pennicillata, containing the soft-bodied non-calcified millipedes with tufts of modified setae, which comprises only one order, Polyxenida. The other subclass, Colognatha, contains the familiar millipedes with hard calcified exoskeletons and scattered setae. Colognatha is so diverse that we've had to invent categories. So it is divided into two infraclasses, Pentazonia and Helminthamorpha, which is further divided into two subclasses, Colobonatha and Eunatha, which is further divided into three superorders. The subclass Pennicillata and the superorder Merochaeta contain only one order each. Merochaeta encompassing Polydesmata. So I label them the single order supraordinal taxa. The other supraordinal taxa, Pentazonia, Colobonatha, Juliformia, and Nematophora, contain 3 or 4 component orders, so I label them the multiordinal supraordinal taxa. The indigenous distribution of Diplopoda extends from at or just north of the Arctic Circle in Iceland, Scandinavia, and 2 places in Asia and Russia, southward to Campbell Island, subantarctic New Zealand. The southernmost South American record is from Parque Nacional Alerces in Andean, Argentina, around 1,000 miles north of Cape Horn. There are no native or adventive millipedes in the heart of Alaska, around Anchorage and the Kenai Peninsula. I know because I've been there twice. And aside from Hawaii and Ponape, no native millipedes inhabit islands in the central and eastern Pacific. However, there are plenty of millipedes on these islands, like Tahiti, all originally introduced by man. The yellow areas surrounded by small dots are ones with few, if any, records that need investigation, as does the outback of Australia. The inverted and upright triangles, asterisk, and star denote important fossil sites. The upright triangle in Scotland is where the late Silurian fossils are located today. The area in green, surrounded by small triangles, is the only place on Earth where all 16 orders are indigenous. Now, I got tired of not knowing where the 16 orders do and do not occur, so 6 years ago I mapped their indigenous distributions. 4 orders occur globally, naturally inhabiting all humanly inhabited continents: Polyxenida, Polyzoniida, which is marginal in Africa, Chordiomatida, which is marginal in both Africa and South America, and Polydesmata. All occur in Southeast Asia. Both Polyxenida and Polydesmata, the 2 orders in the single order supraordinal taxa, occur globally and are well represented on all continents. A representative of Polyxenida on the left with a soft body and tufts of modified setae. The Polydesmata on the right is the bright yellow aphyllori in the southeastern U.S. that a graduate student is studying. There are also 4 northern or Laurasian orders: Glomerida, Platydesmata, Julida, and Calopodida, and all occur in Southeast Asia. They had to disperse onto the terrains after they accreted. 6 orders are primarily Gondwanan. Again, all occur in Southeast Asia, being ferried northward on the terrains. Glomeridesmata's range in Asia is projected. Sphaerotheriida, Siphonophorida, also in the southwestern Nearctic or U.S., and the dot denoted by the red arrow is the area of Elacmeplenipes, the world's leggiest animal with 750 legs on one individual, which occurs south of San Francisco Bay in San Benito County, California. Spirobolida, Spirostreptida, and Stemiulida are also primarily Gondwanan. There are only 2 Southeast Asian records of Stemiulida. Spirobolida and Spirostreptida, which are generally larger bodied and more mobile millipedes, have dispersed substantially into the Nearctic. In the east, Spirobolida has even spread into Canada and occurs today north of Montreal, Quebec. Finally, there are 2 relictual orders: Siphonulida, shown by the dots, and Siphonocryptida, shown by the star and outlined areas. It was also recently discovered in Georgia in the Caucasus region, which isn't on this map. Siphonulida is nearing extinction. Its stronghold is southern Mexico, Chiapas, and Guatemala. And there's an old 1890s record from Sumatra, denoted by the red arrow, based on an individual collected in 1888. These are 2 Siphonocryptidans from Taiwan. To my knowledge, no photos have ever been taken of a Siphonulidon, and I don't have one. All the multi-ordinal supraordinal taxa contain 1 northern Laurasian component and at least 1 Gondwanan or primarily Gondwanan component. In Pentazonia, Glomeridesmata is Gondwanan, Glomerida is Laurasian, and Sphaerotheriida is also Gondwanan. All are in Southeast Asia. Representatives of the Pentazonian orders: a Glomeridesmata top left, Glomeridon top right, and Sphaerotheridon bottom row. Both Glomerida and Sphaerotheria can volvate into perfect balls or spheres like the volvated Sphaerotheridon in the lower right. I have seen preserved volvated Sphaerotheridons that approach the size of a baseball or tennis ball. Really large, impressive arthropods. In Colobonantha, Platydesmata is Laurasian, Polyzoniida is global, and Siphonophorida is primarily Gondwanan. All occur in Southeast Asia. Top left is a representative of Polyzoniida. Top right is a cluster of Platydesmata in the common star-shaped configuration with heads in the center, probably feeding on a fungus or lichen. A representative of Siphonophorida on the lower row, and in the nominate family, Siphonophoridae, the anterior margin of the head is prolonged into a pointed beak or rostrum. In the other component family, the head is not extended. In Juliformia, Julida is Laurasian, and both Spirobolida and Spirostreptida are primarily Gondwanan. All occur in Southeast Asia. Juliformians are long cylindrical millipedes that are rounded in cross-section. Top left is a representative of Parajulidae, the dominant Nearctic millipede family, with males possessing enlarged first legs for clasping the female during mating. The gonopods, or male genitalia, are located in the gap of legs on segment 7, as millipedes are progoniate, with the reproductive tracts opening anteriorly on the body rather than caudally, the opisthogonate condition. A Spirobolida is top right, and two Spirostreptida are on the bottom, a smooth-bodied one of the nominate suborder at left, and a rough one of the suborder Cambalidea with exoskeletal ridges and crests on the right. In Nematophora, Calopodida is Laurasian, Chordiomatida is global, and Stemiulida is Gondwanan. All are in Southeast Asia. Top left is a representative Calopodidon, Abacion magnum, which is common in the eastern U.S., and it too is rough-bodied with exoskeletal ridges and crests. Top right is a Chordiomatida, and two representatives of Stemiulida are on the bottom row, a whole-body photo and a close-up of the head. Stemiulida are easily recognized by one or two large ocelli in the ocular position. This one has two ocelli, a smaller one below the large one. So to summarize, we have a monophyletic group of poorly vagal organisms that is distributed globally and was fully developed with diplosegments by the late Silurian 420 million years ago. Consequently, its origin had to be prior to the late Silurian and in the south, on Gondwana 1, because drift patterns ran from south to north. What we need is a vehicle prior to the late Silurian to ferry ancestral forms from Gondwana 1, the only southern landmass at the time, to the northern microcontinents, and the only such vehicle that also is timely was the Avalonia terrain, which is represented today in northwestern Europe and northeastern North America. Avalonia rifted from the Proto-Africa South American sector of Gondwana 1 480 million years ago, drifted northward for 30 million years, merged with Baltica 450 million years ago, and Baltica plus Avalonia subsequently merged with Laurentia, forming Euramerica 10 million years later, or 440 million years ago. I contend the Diplopoda had to originate on Avalonia itself or very close to it, for populations of ancestral stock to be both present and established on both Avalonia and adjoining Gondwana 1 when Avalonia rifted. If the origin had been on the opposite side of Gondwana 1, I doubt that the stock could disperse that far and even reach Avalonia before it rifted 44 million years later, and substantial and established populations had to exist on Avalonia, not just a few straggler individuals. The only way this could happen was for Avalonia to also be the place of origin. Here are sketches depicting my hypothesis, assuming origin directly on Avalonia itself. Top left, 524 million years ago in the late Cambrian, an ancestral form shown by the bold arrow, and we don't know what it was, crawled out of the Panthalastic Ocean directly onto the Avalonia terrain, then part of the Proto-Africa, South America sector of Gondwana 1. It found an empty earth. All subsurface niches were vacant and available to be occupied. A burst of evolution followed as ancestral stock rapidly radiated into these niches and simultaneously dispersed beyond the future rift line onto Gondwana 1 itself. Top right, 480 million years ago in the early Ordovician, Avalonia began its 30 million year drift towards Baltica by rifting from Gondwana 1, thereby partitioning the original ancestral stock. Some of it was carried northward on the terrain, and some was left behind on Gondwana 1. This rifting event occurred 44 million years after Diplopoda arose, and it is reasonable to assume that most, if not all, subsurface niches on the terrain were fully occupied by that time. Evolution must have stagnated on Avalonia during the 30 million years it was drifting, but the forms left behind on Gondwana 1 were not so encumbered, and continued dispersing, evolving, radiating into additional empty niches, and diverging during these 30 million years. With a 30 million year head start on evolution, one would expect greater diversity in Gondwanan taxa than in Laurasian taxa, and this is indeed true at the ordinal level, with 6 primarily Gondwanan orders opposed to only 4 northern or Laurasian ones. Bottom left, 450 million years ago in the mid-Silurian, Avalonia merged with Baltica, and the stock, whose evolution had stagnated for 30 million years, dispersed onto Baltica, where again it found an empty land, with all subsurface niches vacant and available for occupation. Another burst of evolution followed as Avalonia stock radiated into the vacant Baltica niches, and it is on Baltica during this burst of evolution that the 4 northern Laurasian orders probably arose. Simultaneously, the stock on Gondwana 1 continued evolving, radiating into additional niches and dispersing farther into the continent, and moving in the direction of eastern Gondwana 1 to be present on the land that would break into the eastern and southeast Asian and Indonesia terrains. Bottom right, 10 million years later and 440 million years ago, Baltica plus Avalonia merged with Laurentia to form Euramerica, and the stock on Baltica plus Avalonia dispersed unto Laurentia, where it again found an empty land, with all subsurface niches vacant and available for occupation. Another burst of evolution followed as stock on Avalonia plus Baltica radiated into these vacant niches on Laurentia. The Scottish fossil site of today, shown by the triangle, was then on the margin of Laurentia. So ancestral millipedes arrived in the area of this site 20 million years before they fossilized. While this was occurring in the north, the forms on Gondwana 1 continued evolving, radiating into additional niches and dispersing, reaching eastern Gondwana 1 and populating the terrains that will form eastern and southeastern Asia and Indonesia. Fast forward to the late Carboniferous, 306 million years ago, when West Pangaea was assembling. Siberia and Kazakhstania have merged and subsequently combined with northern Euramerica, whose millipedes dispersed onto Siberia plus Kazakhstania, again undergoing another burst of evolution as they radiated into, occupied its vacant niches, and they are now in position to disperse onto the eastern and southeastern Asia terrains when they accrete. The terrains are approaching, lined up like train cars, and carry Gondwana 1 millipedes. Meanwhile, in the south, Euramerica with its millipede fauna has merged with the Proto-Africa South America part of Gondwana 1 with its Gondwanan fauna, and a mini burst of evolution occurs as stock on both land masses mix, now being able to disperse into the other and penetrate its vacant niches. Millipedes were in both areas, but they were different, perhaps employing different burrowing mechanisms, and hence occupy different niches from the forms that were established in each area. This probably explains the occurrence of 9 endemic families today, in Mexico, Central America, and the southwestern U.S., 4 in Polydesmata and 5 in Spirobolida. Color coding the Diplopod taxonomy. The categories in red, which includes all supraordinal taxa and 4 orders, Polyxenida, Polyzoniida, Chordiomatida, and Polydesmata, occur globally. They had to be fully evolved and exist on both Avalonia and Gondwana 1 before Avalonia rifted in the early Ordovician, so as to be partitioned by the rifting, with some stock being carried northward on the terrain and some left behind on Gondwana 1. Since Diplopoda originated 524 million years ago, according to Pisani's molecular studies, and the rifting event occurred 480 million years ago, their ages are between 480 and 524 million years. The categories in blue, the orders Glomerida, Platydesmata, Julida, and Calopodida, are the northern Laurasian orders. They had to originate after Avalonia rifted, on either Avalonia itself or on Baltica after it merged with Avalonia, and as I've said, they surely arose during the burst of evolution on Baltica after it merged with Avalonia. These taxa are therefore less than or equal to 450 million years old. The categories in green, the orders Glomeridesmata, Sphaerotheriida, Siphonophorida, Spirobolida, Spirostreptida, and Stemiulida, are the primarily southern Gondwanan taxa that had to arise on Gondwana 1 after Avalonia rifted. Their ages are less than or equal to 480 million years. And we don't have enough information or data on the 2 relictual taxa in black, Siphonocryptida and Siphonulida, to infer ages and places of origin. So this hypothesis, supported by the documented distributions of the 16 orders and all higher hierarchical taxa, explains indigenous distributions and, most importantly, accounts for the late Silurian 420 million year old fossils. It places ancestral millipedes in Laurentia, where the Scottish site was then located 440 million years ago, or 20 million years before fossilization occurred. I think this scenario, or one very close to it, must have taken place, because if a completely different scenario had occurred, millipede distributions today would be vastly different, and Diplopoda would probably be substantially less diverse. I do not know histories of other poorly vagal soil organisms, but I do know that very few evolutionary scenarios lead to global distributions of animals that can neither run, fly, swim, nor float. So, could this scenario for millipedes, or at least parts of it, constitute a model for such organisms, particularly ones that don't or only rarely fossilize? I only raise the question and leave the matter to specialists in these groups. The question also arises as to whether there might be marine millipede fossils. None are known, and I don't think any will ever be found. The reason is simple. The strong diplosegment condition, with alternate segmental joints rigid and incompressible, would not convey a selective advantage for burrowing in wet, comparatively soft marine sediments. Flimsy worms and a host of soft-bodied marine organisms readily burrow into soft marine sediments. The diplosegment condition logically evolved on land for burrowing into hard and comparatively dry terrestrial substrates, because on land it does convey a selective advantage. I conclude with a quote from George Byers, retired entomologist at the University of Kansas, who said this in an article on scorpion flies, or the insect order Mecoptera. It applies equally well to millipedes in the hypothesis I have outlined. There were no eyewitnesses to the evolutionary changes or the geographical movements hypothesized here. It is nonetheless enjoyable, and perhaps even somehow intellectually worthwhile, to think about these things and draw inferences. Thank you for your time and attention.